There you go.
Okay, so we're gonna have an experiment here. I have a beaker with water and a soda can. And the soda can has 3 holes on the bottom. So when I bring this up a little bit, not outside the beaker, but just a little bit, you know, I'm gonna remove the whole can above the water. I'd like to know what you guys think is gonna happen.
Well, until it's completely out, the water is gonna stay in. And then once it's out, it's gonna pour out.
You're gonna- What do you think?
I agree.
You agree with that?
Well, I think it'll pour out as soon as it goes past the water level. It's gonna pour out of the can.
Yeah, I agree. When as soon as I believe when you start lifting it, the water's going to continuously fall out until it's empty.
Okay, so let's see what's gonna happen. 1, 2, 3.
Actually starting.
Was that expected or?
The spin was
Spinning?
not.
No,
Not
spinning.
expected. So let's try again, you know, when sometimes it's just, you know, an accident, right? So let's see again. I'm gonna bring it up. So what do you think is happening?
Can you do it again?
You want to do it again? Okay. 2 times and, Esmeralda, what do you think?
Are the holes on the side or on the bottom?
On the side.
Oh.
On the the lower.
Oh.
3 holes are on the lower side of the can. So let me do again.
They're like on the side, like, okay.
Is that a thing that it turns only one way, or when it gets out, it's been only turning?
I think it's turning only one way.
Isn't it? Is
Isn't
it?
it? So let's try again. Okay, let's observe that. So that's one thing we want to observe now. It's always turning on the same way, or
I'll say it's only that way, cause
only one
yeah,
way?
because
Clockwise the last
but it
time.
has to do with like our position on
Yeah,
Earth.
Right, clockwise. It's always clockwise.
I think it's isn't that because our position on Earth is the same thing with the toilet? Like the water only goes one way, but if you are like in South America, it'll spin the other way.
No way.
Yeah,
That's cool.
yeah. If you go past the equator, if you go past the equator, like water in the toilet
That
spins
makes
the other
sense,
way.
yeah.
So we should go now to South America to test if it's going
Yeah.
to Okay, all right, so let me do it once again and see what happens, okay? Okay, it's
Yeah,
still
okay.
moving that way.
Clockwise, okay.
Yeah, well, do you wanna, see the holes and, you know, observe now closer?
Can I see them?
Okay, there you go. So what do you see? Do you see anything strange? No, nothing wrong? Do you see? The 3 holes, there are 3 holes at the
I'll
bottom?
drink that. The president or each?
Yeah.
They're not, oh yeah, they have a way, they have
The
Direction.
direction,
Yeah.
the hole has a direction,
Yeah.
right? So what do you guys think now?
so that's why.
Yeah.
So that's why, right? So the water is going in one direction and the can is going on the other direction, right?
Yeah,
Yeah, 'cause it'll push it.
the hole goes like that.
You want to see in the video?
Yeah, it's smaller.
Yeah, it's a little twisted,
So
right?
it goes this way.
It goes that way. So this is an example of Newton's third law, the action and reaction, right? This is the principle that rockets go in space, right? The same way. You gotta have some mass going in one direction and the other one goes the other direction, okay? So,
So what's the mass that goes in one direction, the rocket?
the explosion of all, you know, gas that goes.
So would you say that the explosion is an actual mass? It's a question.
Yeah, it's produce all that air, right?
Okay.
Okay,
You said Newton's third law is one mass goes one direction and the other goes the other?
Yeah.
Yeah, it's the law of action and reaction, right? If I hit this wall, right? Very gently, right? Very gently, right? I'm not gonna feel much. I feel something, but not much. But if I increase my force on the wall, it's gonna maybe break my hand, right? Okay? So Newton's third law, I think, is the easiest to understand. It's just what we call action and reaction. So let me now talk a little bit about
No.
Newton's first law, right?
Makes sense.
But before that, let me reveal the first thing we learned was that the average velocity is what? What is the average velocity? Average velocity is,
Distance over
Displacement?
yeah.
displacement over
So,
time.
Delta x divided by delta
Delta
t, right? And what that means, what is speed, right? What is velocity? Is the rate of change of some space that you're traveling, right? So how fast am I traveling? So I'm walking this way, right? I'm going, at every second, I'm going a certain, displacement from my original position, right? I'm moving, at a certain rate, right? If I go faster, so that we have to have a way to measure that. How fast are we going? So delta x means the initial final position minus the initial position. And delta t means the time it takes for you to go through that, right? So from here, we came up that x final minus x initial is going to be v times t, right? And then we came up with that equation, x equals, I think we did x 0, right, instead of initial, right? X 0 plus v. So that's the first equation. Then we talk about average acceleration, right? And the idea of acceleration now is different, right? From basically the same thing. It's a rate of change, but rate of change of what?
Over time square.
Huh?
Over time square.
Change of velocity.
Change of velocity, right? Now, here, we are assuming the velocity was constant, right? Initially, right? Was constant. We studied the linear motion, right? Uniform motion, right? So for uniform linear motion, velocity is constant. Now, if velocity is changing, that means it's being accelerated. So the formula is delta v by delta t. And here again, I'm going to have another equation that's going to be v final, v0 plus v.
Is the acceleration vector?
Huh?
Acceleration is a vector.
Acceleration is also vector. Yeah, also vector. Yeah. Because you're accelerating, in what direction, right? I could be, now remember this, I could be traveling in one direction and the acceleration is going to be opposite to that. Okay? Opposite. So this is another form. Then comes the idea that the average velocity is also v final plus v0 divided by 2. So you have two velocities here, right? So the average is the initial, right, plus the final divided by 2. And as I plug in this here, right, knowing that this is equal also to delta, let's put it this way, x final minus x0 divided by t, and then here we can come up with the formula for x final x0 plus v0t plus 1/2 ad squared. Right? If I plug in this here, right, we did this already, right? Plug in here and I calculate for x of f, we come up with this form. Now, Newton's first law is about, it has two aspects, okay? The first one is an object is sitting here on the table at rest, okay? Is not going anywhere, right? It's not going anywhere until we apply a force. But I'm asking you, is there a force right now on this block sitting on the table?
Yes.
Yeah.
Yeah, which one?
Gravity.
Gravity, right? So let's say this block has mass m, so mg, right? That's the forces being applied there. But why is the block not moving?
Because the table is pushing back at it.
Because the table has a, what we call a normal force, right? That is balancing the weight. So if it's the sum of forces applied to this object is 0, right? So this is action and reaction, right? This is action and reaction right here, right? It's like Newton's third law that we just observed there, right? So if it's balanced, right, then it's not moving. Because the sum, this symbol here means the sum of forces is equal to 0. Okay? The sum of all forces is equal to 0. So mg is equal to m. mg is equal to the normal force. Okay? That's the first aspect of Newton's first law. The second aspect is a little more, I think, difficult sometimes for students to understand. Okay? It took me a long time for me to understand. Okay? Now, that is, if I have an object moving at a constant speed, okay? This object is moving at a constant speed. There's no friction here, no friction. Then it will not change its motion unless a force is applied to it. Okay? So if you're in space, for instance, there's no friction there. If I throw this marker this way, what's going to happen? What is going to be the trajectory of this marker if I throw this marker this way?
It's going to continuously move that direction.
That direction, right? But if I do that here in the classroom, what's going to happen?
It's going to fall.
It's going to fall. So in space, no friction, it will continue to move indefinitely. But here on Earth, if I throw that, it's going to have a trajectory. Why do you think it's having this trajectory?
Gravity.
Huh?
Because of gravity.
Gravity. Gravity is a force. So there is an external force on this object here that is pulling this down, and because of that, it's going to fall. And we saw that projectile motion, right? We saw the trajectory, we calculated all that, and we could, when we have projectile motion, we studied on x-axis and y-axis, right? That is not linear uniform motion, right? That is a 2D. Now there are two dimensions, and they are independent. We have to look at them independent. The x-axis, there is no force in that direction. So the velocity here, Vx, is going to be a constant. On the y direction, the Vy is going to change continuously. And because there is gravity acting on it to push it down, right? So that's why the object is going to do this parabola, okay? And it's this one here that is changing. Vx is a constant. Remember, we measure the range, right? If we have the range and we have the velocity, we can figure out the time of the whole trajectory, right? Because Vx is constant, the range is constant, so we get the time of this whole trajectory here. Okay? All right. Now, this is Newton's first law. Second law is basically saying that the force is proportional to acceleration. So force is a vector, acceleration is a vector, right? And there is a proportion here, okay? And that is if I have, if I apply the same force to a truck to try to move the truck, the acceleration is going to be small, right? But if I apply the same force to a Volkswagen, right, my acceleration is going to be higher. Okay? So this proportion is mass, okay? And that comes with the idea of inertia, right? What is inertia? Inertia is the resistance to change, okay? Newton's first law, the resistance to change a body that is not moving, it doesn't want to change, it, status of being at rest, okay? Or it doesn't want to change its uniform motion here, right? The constant velocity. So on both of them, there has to be an external force that is applied that is going to break this balance. Okay, there is a balance here right now. Okay? If I can break this balance, then this object will start to accelerate. So today, on this experiment, is basically about Newton's second law. But at first, I'd like you guys to try to measure the velocity in two different points, and then see if it has changed or not. Okay? The track is an air track. It's a very good way to show when something is moving with no friction. Okay, you can stop.